Good afternoon. Thank you so much. It's a pleasure to be here, especially to be guarded by the divine waves of the Acropolis here in the vicinity. The topic that I will cover today is a technical topic. It's a technical session. And I will discuss about a key capability that we'll have to build up also in the Greek network in order to sustain the introduction of renewables and execute on the roadmap of energy transition. And the topic is called grid forming. Grid forming is a capability that will be needed in inverter-based technologies, such as battery systems, solar systems, HVDC systems, to contribute to the grid stability. And I will explain why this aspect will become important. We'll start with having a look at the energy system in Greece and the market dynamics in Greece. And then I will spend a few brief words on grid stability. Grid stability, and in particular the aspect of inertia. It was brought up by some of the speakers earlier. Why is inertia important? This is one of the few elements of grid stability. And on the broader scope, there are other aspects that are needed to be implemented to have a stable grid in the future. Why is it important for investors in renewable technologies? Because it will allow them to tap into new services that will be introduced in the ancillary support markets. I will also give a status on where we are in Europe with implementing and regulating those features, and I will end off with the key summary and conclusions. This is the system as it stands now in Greece. We have about 17% PV in the energy mix. We have a fair amount of wind, but we also still have a number of conventional energy generation resources based on natural gas, on oil, and this means that we still have quite a leap to take in order to become carbon neutral in the future. If we just look at the PV sector, it would have to double by 2030 as part of the execution plan that was presented yesterday. And this is quite a challenge because if you look at PV today, it already represents about, we said here about 17% PV. We have a build out of 7 gigawatts. We have a total capacity of 24 gigawatts. So let's say one-fourth is attributed to PV in the system. How does it translate into the markets? Here I've taken the spot market price from last week, as well as the various sources of energy that contributed to the electricity that was generated. And obviously, during the day, there are peaks where there is an overcapacity of energy because of the intermittent character of solar and wind. At those times, the prices drop significantly, even till almost zero. And in other periods of the day, the more conventional sources are entering into the mix at more expensive prices. Though there is a larger volatility in the pricing as more we introduce those intermittent renewables. In the last 2 days, we have been discussing many times about the consequences of that, namely the reduction of the curtailment that happens because of the economic mechanism. We have the price volatility, which is a challenge, but also an opportunity for a number of players. Think of the demand response players. And we also discussed at some point in time that curtailment is not only done because of economic reasons, it's also because the grid just cannot support the capacity to transfer the power. So we have an access issue to address. If we look at the grid in a broader perspective, we have to make sure that the grid stays stable. And if I think of all those, let's say, thermal generated synchronous generators that generate electricity, I take sometimes the parallel of a tumbler. It has a kind of massive tumbler that is rotating. It has a mass. It has, when it's rotating, a kinetic energy. And the behavior of the grid is very simple. You have the connected synchronous generators that create a torque which is compensated by the electronic torque. And as long as there is a balance in the grid operates at a stable frequency. And there are two key parameters that drive the stability in the grid in terms of frequency. That's the balance of power, but it's also the inertia constant. So what is the inertia constant? It's basically the time that it takes to dissipate all the kinetic energy in the synchronous generators as the power flows in the grid. And typically, this is in a range of a couple of seconds, between 3, 4, 5, 6, 7 seconds that each generator is contributing to the grid. Now, what happens if we retire synchronous generators? What happens if there is more power flowing from renewable energy? The consequence is that the inertia drops. And here I have demonstrated for Greece and some other countries the distribution of that inertia in terms of seconds as we move towards the transition. We see that the inertia constant is dropping. And the lower that value, the quicker the grid gets destabilized if we have a disturbance happening. Is that important? Yes, because that means that very quickly the frequency drops below a certain number where the loads are getting disconnected and the grid is basically collapsing. I've shown 3 other countries, Ireland, UK, and Germany, that have a similar profile. And all of those companies are taking measures to introduce grid-forming capabilities for inverter-based renewables. I've also shown the country where I come from, here in Switzerland, and there the profile in the future is still, I would say, quite okay from that perspective. Greece seems to be in the category of countries that will have to cope with low inertia. So here I very, in a kind of artistic way, sketch what's happening if we lower inertia. On the top curve, the frequency curve that you see, this is the normal situation. If we introduce renewables and the inertia drops and there is an event happening, an imbalance in the grid, then the frequency will drop much, much quicker. And one of the parameters that is describing that is the so-called ROC-off, the rate of change of frequency. This also comes very high, so that means the frequency drops very fast. And how do we avoid that? Well, there are 2 ways. Either the TSO is installing infrastructure in its grid to compensate that, but in most of the cases, it is relying on the market parties, so the investors in generation, to help support unbalance. And today, most of the services in the ancillary service is based on frequency containment reserves and automatic restoration reserves. In the future, this will no longer be sufficient. We will have to have mechanisms that react much, much faster than in the past. Mechanisms that react on a, let's say, sub-second level, and this is the area of what is called firm or fast frequency reserves. That is already introduced in various markets in Europe. So the systems need to be able to support that, and it will also lead to new service opportunities in the application mix. There is another element, and that's the pink on the left-hand side, that is the support that is needed in a very short time frame, just a few cycles, milliseconds. And this support is needed also by renewables when we are more and more retiring conventional synchronous generators. This inertial support can be enabled by grid forming. That's the core aspect of grid forming. It provides a kind of virtual inertia, substituting the mechanical inertia from the rotating masses of the synchronous machines. Also, this type of services could be procured on the market. Here I've given an overview of all the various grid stability services. Frequency stability I focused on for the virtual inertia, but there are a set of other services that can be procured from the market if they are, of course, introduced by the market players. This gives, again, opportunities for revenues for battery players, provided, of course, they support all of these services. Here I give an example of the UK market that is, from that perspective, more advanced. And you see on the left-hand side the type of services that I have introduced. The inertia service, which is in trial today, the short circuit level support, and the dynamic voltage support. And they have built out a complete framework in order to support that in the future. Where are we in terms of regulation and standards? There is an important standard to be complied to for investors in generation, and that's the requirements for generators. These are being updated to support all those features for grid forming. This is ready to be approved. And then there is a whole set of standards that is following that, which are implemented in each of the various countries. In the middle piece, Germany, Italy, and Spain already have requirements for that. Another element that I wanted to highlight is that a battery system is much more than just a set of cascaded cells. It becomes an IT/OT system that helps to support the grid while it is delivering energy. Summary and conclusions. Grid forming will become a necessary technology to enable the transition, also in Greece. It will allow inverter-based systems, such as battery systems, to support the grid similar as synchronous machines did. It provides virtual inertia and other stabilizing capabilities, and the standards are well underway. The regulations are well underway. From a commercial perspective, opportunity perspective, the key takeaways are the following. BESS, battery systems, can turn imbalance effects into a commercial opportunity under peak shaving or arbitrage. Secondly, if there is a lot of curtailment, it tends to start thinking about co-location of PV plus battery or even hybrid systems. A hybrid system is where the systems are truly integrated. And there is an opportunity to capture revenue in the merchant markets, in particular the ancillary markets, because certainly new services will come. And then finally, if you're investing in storage systems, battery storage systems, think about what stack you want to build up. A combination of services in the energy markets and in the capacity market. And also be aware that over time, the optimal stack will change. So manage your application set well. Thank you.